For decades, the Union Pacific Big Boy ruled America's rails, a steam giant unmatched in power and prestige. Then a radical diesel prototype emerged. It was a machine so colossal and ambitious that it was meant to erase the Big Boy forever and to rewrite the future of railroading. But within just a few years, this technological gamble unraveled in ways nobody saw coming. What secret flaw doomed the very locomotive that was built to destroy a legend? Steam thundered across the high passes of the American West, and nothing carried more weight, literally and figuratively, than the Union Pacific Big Boy. Designed in the early 1940s for one purpose, these locomotives hauled the heaviest freight over the steepest mountain grades from Cheyenne to Ogden and beyond. Each Big Boy stretched over 132 feet and tipped the scales at more than 1.2 million pounds with tender attached. The heart of this machine was its wheel arrangement of 4884, a configuration that delivered unmatched stability and brute force. Crews relied on its 135,375 pounds of tractive effort to muscle 1,000-ton trains up the Wasatch and Sherman Hill, places where lesser engines stalled and struggled. The Big Boy could generate over 6,000 horsepower, yet engineers praised its sure footing and responsive controls. For decades, it stood as the gold standard, an icon of American engineering, a symbol of industrial might. No other locomotive matched its combination of power, reliability, and sheer presence on the rails. To surpass the Big Boy would require not just more horsepower, but a revolution in how railroads thought about moving freight through mountains and across continents. Railroad executives in the early 1960s faced a hard reality. The age of steam, for all its spectacle, was becoming unsustainable. Fuel costs were climbing, and coal, once cheap and plentiful, no longer offered the savings it once did. Labor expenses kept rising too. Steam locomotives demanded large crews, round-the-clock maintenance, and frequent servicing. Every run meant hours spent in the shop, cleaning boilers, and tending to hundreds of moving parts. Meanwhile, diesel locomotives promised a different future. They could run farther between stops, required fewer mechanics, and consumed less fuel per mile. For railroad strategists, the math was simple. Diesels could move the same freight for less money, with fewer breakdowns and a smaller workforce. The pressure to modernize wasn't just about keeping up with the times, it was about survival. Union Pacific and its competitors needed to cut costs to stay profitable on routes that stretched from the Midwest to the Pacific. The promise of lower operating expenses and greater reliability pushed railroads to seek out the next leap in technology. This urgency set the stage for bold experiments, designs that aimed not just to match the power of the Big Boy, but to do it with a fraction of the overhead. At the Electromotive Division design offices, ambition took center stage. The Electromotive Division engineers set out to leapfrog everything that had come before. Their idea was as bold as it was simple. Take two proven GP35 locomotives, each with its own 16-cylinder diesel engine, and combine them on a single massive frame. The result would be a locomotive with 5,000 horsepower under one hood, a level of power unheard of in a single diesel unit at the time. But raw muscle alone would not be enough. To handle the weight and deliver that power to the rails, Electromotive Division developed a new type of four-axle truck known as the D truck. Unlike anything seen on earlier diesels, these trucks were designed to spread the locomotive's immense weight more evenly across the rails, promising both stability and traction. The DD35A design called for 8 traction motors and a fuel capacity that dwarfed most other engines of the day. Every detail, from the dual-engine layout to the advanced truck design, spoke to a philosophy of building not just a bigger locomotive, but a fundamentally different one. Electromotive Division's team believed that by combining proven technology in a radical new form, They could offer railroads the power of a multi-unit, consist with the efficiency and simplicity of a single locomotive. This was more than an upgrade. It was an attempt to rewrite the rules of American freight railroading. 5,000 horsepower. That number alone set the DD-35A apart from anything else on the rails in 1965. Under its hood, two 16-cylinder diesel engines, each a powerhouse in its own right, worked in tandem, combining their muscle to move the heaviest freight. Locomotive Division's engineers did not just stack two locomotives together. They fused them into a single, seamless machine, stretching over 88 feet from coupler to coupler. The DD-35A's frame carried 572,000 pounds, more than 250,000 kilograms, resting on 8 massive axles. Each axle bore the weight of a small truck, spreading the load across newly designed 4-axle trucks that had never been seen on a diesel before. The fuel tank alone could swallow over 5,000 gallons of diesel, enough to run from Nebraska to California without a refill. 8 traction motors delivered the power straight to the rails, giving the DD-35A the brute force to rival any steam giant. Numbers like these were not just impressive, they were unprecedented. For railroad executives and engineers, the DD-35A seemed less like a locomotive and more like a statement, bigger, stronger, and ready to haul America's freight into a new era. Every detail, from its dual-engine heart to its towering profile, declared its ambition to outclass everything that had come before. Union Pacific's executive board faced a problem that could not be solved by tradition alone. Their fastest freight schedules demanded more power than any single locomotive could provide. The operations team calculated that to keep their signature trains moving at speed across more than 1,500 miles of mountains and deserts, they would need 15,000 horsepower at the head end. This was not just a wish list. It was a requirement set by the realities of modern railroading. The big boy had set the standard, but even its 6,000 horsepower could not meet the new demands without running in multiples or mixing with diesels and turbines. Crews juggled combinations of gas turbines, SD-24 diesels, and whatever else was available, but the system was complicated and expensive to maintain. Schedules slipped and costs rose with every extra locomotive added to a train. Union Pacific's solution was bold. Invest in a new generation of power that could deliver unprecedented muscle in fewer units. The company issued a challenge to locomotive builders. Design an engine that could be the backbone of a 3-unit consist with 15,000 horsepower. Locomotive Division's answer was the DD-35A, a 5,000 horsepower diesel that could be paired in sets to hit the target. This was more than a technical experiment. It was a calculated business decision. Union Pacific believed that by reducing the number of locomotives needed for each train, they could streamline operations, cut labor costs, and simplify maintenance. The railroad committed to the DD-35A project not as a gamble, but as a strategic bet on the future of American freight. With the order placed, Union Pacific signaled its willingness to move beyond steam and to put its trust and its reputation on the line for the promise of raw diesel power. Test runs began with high expectations, and for a moment the numbers seemed to justify the gamble. Early on, the DD-35A matched the big boy's legendary tonnage, pulling mile-long freights over the same mountain grades that had defined steam's reign. Crews reported the new diesel could move 3,600 tons up Sherman Hill without breaking a sweat, a feat that once required the full muscle of a big boy. Fuel logs painted an even brighter picture. On runs between North Platte and Ogden, the DD-35A burned less diesel per mile than the coal and water the big boy devoured, all while running with a smaller crew and fewer service stops. Engineers marveled at the smoothness of the ride and the instant power available from those two 16-cylinder engines. Maintenance teams, used to the constant grind of cleaning and oiling steam machinery, found themselves with more time between overhauls. For the first time, Union Pacific could boast a single locomotive that combined the raw strength of its steam past with the streamlined efficiency of diesel technology. In the yards and on the main line, the DD-35A looked like the future in motion, delivering on its promise to haul more freight, more efficiently, and at a lower cost. For a brief window, hope ran high that this machine would set a new standard for American railroading. Shop doors closed more often than expected as the DD-35A's true nature revealed itself. Mechanics logged a string of electrical faults, short circuits in the traction motors, relays that failed without warning, and control cabinets plagued by persistent moisture and dust. The dual-engine setup, once hailed as a breakthrough, doubled the number of potential failures. If one engine faltered, the second rarely picked up the slack without issue. Crews grew frustrated as power cut out stranded loaded freights on remote stretches of track, sometimes for hours. Electrical lockers, crammed with wiring and relays, became notorious for overheating and blowing fuses. Maintenance supervisors reported that sand meant for traction on icy rails leaked into sensitive electrical compartments, causing mysterious shutdowns that left even veteran electricians scratching their heads. Each trip to the repair bay seemed to uncover a new gremlin. Instead of setting a new standard, the DD-35A was building a reputation for unpredictability. The promise of seamless diesel efficiency faded, replaced by a growing sense of unease among the teams responsible for keeping these giants on the move. Inside the maintenance shops, frustration grew with every DD-35A that limped in for repairs. The promise of streamlined upkeep vanished as soon as mechanics opened the hoods. Two full-size diesel engines meant twice the filters, hoses, and pumps. Double the work just to keep the basics running. But the real headache came from the locomotive's mixed heritage. EMD had built the DD-35A using whatever parts were available, including traction motors salvaged from retired Alco and GE units. This patchwork made sourcing replacements a scavenger hunt. Mechanics sometimes waited weeks for the right motor or electrical component, watching deadlines slip and costs pile up. Even simple repairs turned into all-day affairs if the right part was not on hand. Shop foremen juggled orders from multiple suppliers, trying to keep enough spares on the shelf for a machine that did not match anything else in the fleet. The hybrid design, meant to save money, ended up driving expenses through the roof. Every breakdown forced the railroad to choose between paying a premium for rare parts or sidelining the locomotive altogether. The DD-35A, instead of simplifying operations, created a logistical nightmare that no amount of overtime could fix. Track inspectors sounded the alarm as soon as the DD-35A started running heavy freights across Union Pacific's main lines. Each locomotive weighed nearly 572,000 pounds. And the new four-axle trucks, meant to spread the load, could not keep up with the punishment. Rails that had handled decades of big boy traffic began to show signs of accelerated fatigue. Welds cracked, joints loosened, and maintenance crews found themselves replacing sections of rail far more often than before. The pounding was not limited to the tracks. Bridges, some built in the steam era, groaned under the concentrated weight. Structural engineers logged fresh stress fractures in girders and supports, forcing urgent inspections and costly repairs. Way department records from the late 1960s show a spike in rail replacement and bridge reinforcement projects wherever the DD-35A ran. The economic promise of the new diesel was being eaten away by emergency infrastructure spending. For every mile the DD-35A saved in fuel or labor, it took back twice as much in steel and overtime for track crews. The railroad's bottom line suffered, and the men tasked with keeping the rails safe began to question whether any savings were worth the damage left behind. While the DD-35A faded into obscurity, the big boy's reputation only grew. Museum curators and rail fans kept the memory alive, preserving surviving locomotives as symbols of a different kind of engineering wisdom. Union Pacific 4014, once destined for the scrapyard, found new life through a painstaking restoration, returning to steam in 2019. The sight of 4014 thundering across the plains drew crowds by the thousands, a living reminder that thoughtful, proven design can outlast even the boldest experiments. The irony was hard to miss. While the diesel prototype that promised to make legends obsolete was quietly forgotten, the big boy rolled on, celebrated not just for its size, but for its lasting impact. In the end, the machine built to be replaced became the one that endured. Modern engineers studying the DD35's fate draw one lesson above all. On paper, raw power means little if a machine cannot be kept running in the real world. The DD35A dazzled with its horsepower and scale, yet its dual-engine design created twice the headaches and endless parts shortages. By contrast, the EMD SD40 series, introduced just a few years later, found success by focusing on simplicity and serviceability. The SD40's single-engine layout, standardized components, and ease of maintenance made it a staple for decades, while the DD35A quickly vanished. Today, design teams point to these two locomotives as case studies. The SD40 proved that reliability and maintainability often matter more than headline-grabbing specs. The DD35A's story is now taught as a caution. The best engineering is not always the boldest, but the one that works day after day, year after year. Most of the DD35A fleet met a quiet end. By the mid-1970s, Union Pacific had pulled nearly all units from service, citing high costs and chronic downtime. Scrapping records show that every DD35A cab unit and booster was cut up for metal, and the work was completed in 1981. No DD35A survives on display or in preservation. Their frames and engines were recycled or cannibalized for parts, leaving behind only photographs and a few scattered components in private collections. In contrast to the big boy, which drew crowds in museums and on special excursions, the DD35A vanished almost without a trace. Preservationists tried to save at least one example, but interest and funding never materialized. The promise of revolutionary power faded into memory, and the physical machines disappeared along with it. Innovation still tempts us to build bigger, faster, and stronger, but real progress demands more than raw power. Today, railroads prize reliability and efficiency, not just spectacle. The DD35A's fate is a warning. Ambition without practicality leaves only abandoned giants behind. In every industry, the true test is not what we can build, it is what endures. What survives shapes the tracks we lay for the future. Share your thoughts below.